We have learned already that large residuals can be an indication that something is wrong with either the observations or the mathematical model. In this video, we will introduce the criterion in order to decide when the residuals are too large, which means that we suspect the presence of an error not being in the normal range of the random errors. What we will do is to introduce the so-called overall model test. We will do this in a rather intuitive manner, and our point of departure will be the example as shown before. This graph shows the observed heights, the estimated trend line, and the corresponding residuals. Also shown are the 95% confidence intervals of the observations. In other words, there is a 95% probability that the random errors are not exceeding the bounds of these error bars. The residuals are in fact the estimated errors. In this example, the residuals are all well within these bounds, so this is an indication that no other errors are present. Now look at the example with the third observation being an outlier. Here we show the residuals with a slight offset in order to see that indeed the residuals in the figure on the right are exceeding the limits of the error bars for 3 out of 4 observations. In other words, the estimated errors are outside the expected range for the random errors, which is an indication that another type of error must have been present. But looking at this example, you may see a problem with the approach to evaluate each individual residual, since the outlying third observation in fact causes the residuals of the other observations to be very large as well. Furthermore, if one residual is exceeding the confidence bounds, it does not immediately imply that it is due to a bias. Therefore, a better approach is to look at the weighted sum of squared residuals. Intuitively, this makes sense, since, first of all, we are then still comparing the size of the residuals to what we expect based on the precision. Secondly, this weighted sum of squared residuals is what is minimized in case of best linear unbiased estimation. We say it provides the best fit. This logically implies that a large value means a bad fit. Finally, the weighted sum of squared residuals takes into account all residuals, which is important. Remember the example with one outlier, resulting in large residuals for the other observations as well. Let's have a look at the weighted sum of squared residuals for the specific and very common case that the covariance matrix QIY is diagonal. Then we will get this. And if we work this out, we will get this result. It is the sum of what we call the squared relative errors, where we define the relative error as the ratio of a residual with the standard deviation of the corresponding observation. So indeed, we are still comparing the size of the residuals with the expected deviations due to the random errors. Our initial question has thus changed from when are the residuals too large to when is the sum of squared residuals too large. In order to answer this question, we will have to look at the statistical distribution of this variable. We will refer to it as the test statistic and denote it by T. Note that we use the underlining here since we are now looking at the stochastic variable and not a particular outcome. We know that our estimators are normally distributed. Of particular interest here is E hat. But test statistic T is not a linear function of this normally distributed vector. So T will not be normally distributed. However, it can be shown that T has the so-called chi-square distribution. To be precise, it is the central chi-square distribution with m minus n degrees of freedom. And recall m minus n is the redundancy. Here we show some examples of chi-square distributed variables with 3 and 10 degrees of freedom. Knowing the distribution of a random variable allows to evaluate the probability alpha that an outcome or realization will exceed a certain value k as visualized here. The red area is thus equal to the probability alpha that an outcome is larger than k. Vice versa, we can also choose a probability and calculate the corresponding k. What we will do is to set the probability alpha equal to a small value and then calculate k. If then we have a certain realization of t based on the observations we collected, we can check whether it is larger than k. We know this is unlikely to happen since we chose a small probability alpha. Therefore, we conclude that something must be wrong with the observations or our model if t is larger than k. The test procedure just described is the so-called overall model test. In summary, for an estimation problem, we will have our nominal mathematical model. We collect our observations y, then apply blue to get estimates x hat and corresponding residuals e hat. We calculate the test statistic t being the weighted sum of squared residuals. And knowing that t is a realization of a chi-square distributed variable, we choose a small probability alpha and determine the corresponding threshold value k, such that we believe that it is highly unlikely that t will be larger than k. If we do find that t is larger than k, this is an indication that something is wrong with either the observations or the model we used. In the next video, we will give an outlook on what to do in this situation.